In activity 3, we're going to look at acceleration. And acceleration is something we are familiar with. We've been talking about it since a young age, and it's something that we experience every day, especially like when we're in a car. We can accelerate. We know we accelerate when we start, and we usually call when we slow down deceleration, but here we'll call everything acceleration. But even in our everyday movements, when we move our hands, when we walk down the hall, we're accelerating and decelerating. So what it is it's actually a velocity change, and acceleration is how quickly that velocity changes, or we'll say the rate of the velocity change. But it's also the change in velocity over change in time, because that's going to tell us how much the velocity is changing for a unit in time. Is telling us how quickly that velocity is changing. In this class, we're going to look at the constant acceleration. So in real life, we don't usually have constant acceleration, but it's a simplified way so that we're changing our velocity by the same rate in a problem. So that means that the velocity is changing at a constant rate. So if we have constant acceleration, that means that we'll get a straight line on a velocity time graph because the velocity is changing by the same amount every second. So just like when we were walking at a constant velocity, we had a straight line because our position was changing by the same amount each second. Here, the velocity is changing by the same amount each second, and I get a straight line. So let's actually see what this physically looks like. If I was moving with a constant velocity, so let's just say this, we have constant velocity. So our velocity is not changing at all. That means no acceleration. I'm just going to put no A, and I'm going to put an arrow above acceleration because acceleration is given by the symbol A, and it's also a vector, so it will have direction. So if we have a person walking at constant velocity, they're not changing their velocity at all, that means that every second they're going to be going the same distance. So let's say they're going 2 meters every second. We'll say this is meters. So in this case, my person is at 0 to start. At 1 second, they're at 2, and then the next second they go another 2 meters, and then the next second they go another 2 meters, and the next second they go another 2 meters. So they're evenly spaced out. They're always going the same distance. So this one down here will be with acceleration. So let's say they start out very slow, so they only go half a meter to start, and then the next second they end up going a full meter, and then the next second they end up going 2 meters, so they'll go from 1.5 to 3.5, and then the next second they go even faster, so they cover more than 2 meters. So let's say they go 4 meters, so they'll be at 7.5. So what we see as that person gets faster and faster, the space, the distance they go every second is increasing. So these diagrams are really helpful. They're called motion maps. They show you where an object is every second. And if they're going the same distance every second, then that's constant velocity. You'll see a nice evenly spaced motion map. And if they're accelerating, what we'll see is they'll start out going just a little bit in the first second, and then a larger distance in the second, and then an even larger distance in the third, and an even larger distance in the fourth. So you see them gradually getting, if you take a snapshot of where they are every second, you see them getting further and further apart every second. So these are motion maps. They're not in the module, but they're very handy, and a lot of physics extra help websites will use them. because they're a good way to get a quick snapshot of what's happening. And you can really easily see the distance covered every second. So when you see that position, you can see how far they've gone every second because it's 1 second intervals. It really does show what's happening. So constant velocity, they just move the same amount every second. With acceleration, they're going to move further and further with every second. So the last thing that I wanted to do to introduce acceleration is go over how to calculate it. We're actually mostly going to use this blue method of calculating, but I just wanted to also go over another way that you can calculate it. So we can see if we plot a velocity time graph, we can see how the velocity of the object is changing every second. When we have acceleration, they're getting faster and faster every second. So this is not a position time graph. If this was a position time graph, this would be constant velocity because the position would be changing by the same amount. But when the velocity is changing on a velocity time graph, then we see they're speeding up and they're getting faster. Their velocity is increasing. So we could find the slope of this, and that would tell us the acceleration because that's telling us how much the velocity is rising over each unit of time. So that is one way. You might see that in your future studies. We will, for the most part, be using the formula. We can find the average acceleration if it's not constant, but if we have constant acceleration, whatever your acceleration is, it's the same at all times, so we don't need to average it. So we could, if it's constant acceleration, we just find acceleration. And it's equal to the change in velocity over the change in time, or we can call this the time interval. Now, one thing before we start doing some examples, I just wanted to go over the units for acceleration. They are a little bit tricky. They sound weird to start, but they do make sense if you think about it. So my velocity is changing each second, and my velocity is in meters per second, or meters per second, and that is changing every second. So how much is my velocity in meters per second going up? Every second. And here it's just below 1. So we say the amount the velocity is changing is meters per second. That's changing each second, or meters per second second. We can also say meters per second squared. And then the last thing that I will add in here is we do need to have a direction with acceleration because it is a vector quantity. And we do give it the symbol A. And it looks like I accidentally wrote that twice, but that's how important it is. It's a very important point that acceleration is a vector. Let's look at some examples now. So we'll look at 2 examples. The tricky thing is when using this formula, when we are using the formula, acceleration is equal to the change in velocity. So what we're going to have to do for this is subtract final velocity minus initial velocity, and we will include a direction. And then quite often they just give us the time interval, so the time that happens over. But if they give us 2 different times, we could also subtract them. So we could do the final time minus the initial time. But quite often they just tell you what that time interval is. The other tricky thing about these questions is sometimes your velocity is 0 and they don't tell you that in the question. So we have to look for words that mean the velocity is 0. So in my first question, it says that the motorbike is starting from rest and undergoing uniform acceleration, and it reaches a final velocity of 21 meters per second north and 8.4 seconds. So we want to find its average acceleration. So we're going to use the grasp method. We want to list our givens and requireds, and then we'll analyze with the formula. We have our formula over here, and then we'll sub in and solve and write a paraphrase or a statement. So let's just quickly list what we know. We only have two numbers here. We have this final velocity of 21 meters per second north. And we don't have a starting velocity, but if you notice in the question, it says that it's starting from rest. Rest means it's not moving. So anything that's not moving has a velocity of 0. And since this is our starting velocity, that's our starting velocity is going to be 0. And then they give us the whole time that this takes. So that's just the time interval, that 8.4 seconds. And we need to find our acceleration. So once we have listed everything, this is a really key step when you're doing acceleration problems, to list everything, because it will really help you out. And once we have that, then we can just take our formula that we have up here and sub in and find our acceleration. So they gave us that whole time interval, but we do need to figure out what our change in velocity is with our final minus our initial. So we'll have to subtract those two. So I'm going to take my 21, so we will do the final minus the initial. So we will take our 21 first, and then we'll subtract 0. And then we'll divide it by our time interval, which is 8.4 seconds. So on top, we will just get 21 minus 0 is 21. And make sure you do that subtraction first and then divide second. That's our little bit of bed mass from a while ago. So that's going to be 2.5 meters per second squared. So what this means is another way of writing this is meters per second. So it means every second, each second, the motorbike is increasing its velocity. Because it's positive, it's increasing its velocity by 2.5 meters per second. So if it started from rest, we could actually show that, I'll just erase this because it's running into our other problem, but at rest it was 0 meters per second north. And then at 1 second, it would be 2.5 meters per second north. And then the next second, it's increasing its speed by another 2.5. So it would be at 2 seconds, it would be 5.0 meters per second north. And I could keep going at 3 seconds. It would be another 2.5 meters per second. So it would be 7.5 meters per second. So the acceleration just tells us how much its velocity is changing in meters per second every second. So as each second passes, it's increasing its velocity by 2.5 meters per second. So 2.5 meters per second per second. And then we can write a paraphrase. Therefore, the acceleration is 2.5 meters per second squared. I like it just to write it as meters per second squared in my paraphrase because it makes it a little bit shorter to write. So hopefully that gives you a picture of what's actually happening with the velocity. Let's try another problem. So this time we have a cyclist traveling smoothly. So I'm just going to undo that for 1 second. All right, so let's start that one over again. So we have a cyclist traveling initially at 14 meters per second south, and it stops in 4 seconds. So automatically, as soon as I see meters per second and a direction, I should be thinking this is velocity because meters would be distance or displacement. Meters per second is how fast I'm going. So that would be a velocity if it has a direction. And that's what I'm starting with. That's my initial velocity. So always, we'll do a summary chart actually of how to tell the different quantities by the units, because they often in a problem will give you the units. And then it's braking smoothly and stops in 4 seconds. So that's the whole time interval. That's how long it takes. And we want to find the acceleration. So we're almost there. We know our time interval, we know one velocity, but we don't know the second velocity. So this is where we have to be careful again. They often have a 0 velocity hidden in here. And if it's at rest or stops, then that's going to be 0 velocity. And this is, since it's coming to a stop, its final velocity is going to be 0 because it's going to stop. So we can list our givens. We know our initial velocity is 14 meters per second south, and then our final velocity is 0, and our time interval is 4 seconds. So we want to find our acceleration. So we're going to use that same formula. A is equal to delta V over delta T, but our final velocity as minus our initial velocity will be equal to our delta V. So we'll just put that in put this VF minus VI in for the delta V. And then I'm ready to put in what I have up here as my givens. So this one is a bit tricky because now it's my final velocity. That's 0. So I'm actually going to be starting with 0 and subtracting my initial velocity, which was 14 meters per second south. And I could put my time interval in as 4 seconds. So when I actually calculate that, when I do the subtraction, 0 minus 14 is negative 14 meters per second south. And this all happens in a span of 4 seconds. So what that means is my acceleration is actually going to be negative, and it's going to be negative 3.5. So what does that mean then? If I have a negative acceleration, is that positive, or is that possible? And it turns out it is. So that means what happened is I started off at 0 seconds, and my velocity was 14 meters per second south. And then what's happening if I have a negative velocity is that, or negative acceleration, now this velocity is decreasing each second. And sorry, I've got a little bit excited about explaining the negative. It should be meters per second squared, or negative 3.5 meters per second per second. So every second I'm going to take away 3.5 meters per second. So if I go to 1 second, it's going to be 10.5 meters per second south. And then if at 2 seconds, my velocity is going to be, I'm going to take away another 3.5. So that's going to get me to 7 meters per second south. And at 3 seconds, I'm going to take another 3.5 away. So that'll leave me going only 3.5 meters per second south. And then at 4 seconds, I'll have taken away another 3.5 meters per second, and I'll have 0 velocity, which is what happened in the problem, right? We went from 14 down to 0 in 4 seconds. So it takes a little bit of understanding what that number physically means for it to make sense. But if you think of it as I'm either adding a velocity every second or taking away velocity every second, then it can make sense.